Today, we're talking about valve applications in the biopharm industry, specifically clean air and gas applications in upstream cell culture. And that means that for cell culture, we're going to talk specifically about applications in the incubator suite and also the bioreactor suite. And with that said, let's get going. This is my depiction of an incubator suite. Just a couple of things about that. Incubators are typically glass and stainless steel cabinet-like devices, and inside of which the cell cultures in either beaker or bag form are placed on shaker tables. The incubator has its own environment, and usually gases that are supplied in that environment are O2, CO2, and clean compressed air. Tubing from a wall panel leads typically to the incubator. The flow control in incubators is usually done by solenoid valves, and the gas is pulsed in at a flow rate that keeps the incubator space at a certain pressure. And it is usually in single-digit millibar or inches of water pressure. As far as valving goes, there's always going to be, coming off that wall panel or off the ceiling in some cases, a sanitary ball valve, usually a half or 3/4 inch sanitary tri-clamp ball valve that will always be there. Downstream of that, you're going to have a PRV. Interestingly enough, the pressure that the regulators are set at is usually about 20 psi or about 1.1, 1.2 bar. I found that surprising because I know that incubators themselves are, the pressure inside is, again, millibar or inches water column. But the solenoid valves, the pressure drop across that will take care of that final pressure drop. So on this application, on incubators, you will probably be able to use just our JSR LF, which is the small little valves that I'm pointing at here, or the JSR. These are our lower flow valves. You probably won't need this valve. It's actually the same platform, but with a bigger diaphragm. And so these valves are all you'll need typically at an incubator. That being said, let's take a look at our valve offering so that you can understand what the valves are. So we make valves at very low pressure up to high pressure and very low flow to high flow. And I've positioned all these on this chart so that you can see which valve is what. So the JSR LF low flow ULP, that's ultra low pressure, and the JSR ULP are the lowest pressure valves that we offer. And these are, again, in single digit millibar up to 25 psi max. The JSR LF LP, low flow, low pressure, or the JSR low pressure. These are low flow and low to medium flow valves. And these have the lowest nominal set point is 1 psi. We've set them obviously in a video. We go down to a half psi on set points. The JSR LF, this is JSR low flow and JSR. Then we have the JSR H and HF, high flow. These are our highest pressure setting valves. You can set these down to a minimum of 5 psi all the way up to about 150 psi if needed. These JSR H and HF are typically going to be used on distribution lines for knocking pressure down if that's needed. Typically not point of use valves for these. All right. That being said, let's look at the bioreactor suite. So here's a typical stainless steel bioreactor with a schematic, and you can see the gas coming in at the left over here, clean compressed air, O2. CO2 is typical. Sometimes you'll see a nitrogen valve there. Most often it's these three. The gas comes in, goes through valves, goes through mass flow controllers, typically a Bronkhorst or a Brooks type flow meter. And then the gases combine, go through a sterile filter, and then the gases go through a line into what's called the sparge. And the sparger is a little device at the bottom of the bioreactor. It's tubed to the bottom. And this is what oxygenates and provides oxygen to the bioreactor broth. So it bubbles up, all those gases bubble up. If I'm putting bubbling gas into a bioreactor, I've got to be able to vent that gas off. And you'll see a sterile vent filter on bioreactors, maybe two, because sometimes they worry about foaming events blocking the filter. And then you may or may not have a back pressure regulator at the end. And we're going to go through this in more detail. Here's the same thing, but a single-use bioreactor. This is what the schematic looks like. All right. These are photographs of what these bioreactors actually look like in the field. And they come in all different shapes and sizes, from very small 10-liter up now to 6,000 liter. Is the 6,000 liter is the largest bioreactor bag to my knowledge anyway. All right, valving on this, again, we've got ball valves. You have to have a shutoff valve, sanitary ball valve on these 1/2 or 3/4 inch lines. And that's the same up here. You'll notice on the stainless bioreactor, I may or may not have a nitrogen line coming to the top in the event that they want to add nitrogen to the headspace on top of the bioreactor broth, on top of the fluid. But you're going to have a shutoff valve, a sanitary ball valve. All right, and then we've got PRVs. PRVs are going to be typically on stainless bioreactors, the JSR LF and JSR. These little guys are going to be fine for reducing the bioreactor gas pressure. And the same is going to be true on the nitrogen line. In this case, if they're adding nitrogen to the top, that valve actually may be a lower pressure valve like a JSR LP, but that would be all that would be needed. Let's look at the single-use bioreactor. Same thing, same setup actually. The stainless steel infrastructure, if you will, that feeds the gases and also feeds all the fluids in, that's going to be stainless steel. It is from there that they'll hook single-use tubing up, and from there on, it's single-use tubing to the single-use bioreactor bag. All right. You'll notice here at the top, single-use bag inflation. This is pretty typical. So on bags, usually 500 liter and larger, there will be a facility for inflating the bag with gas prior to filling with Wi-Fi, growth media, and other fluids. So at the beginning of the batch, before they actually fill with ambient WFI, they will pressurize this bag. Usually 500 liter bags are going to be pressurized about maximum operating pressure on a 500 liter bag, typically about 0.3 bar, so about 5 psi. On larger bags, the max pressure can be as high as 3 psi, but this valve, this pressure will be set lower than that. So I'm going to have ball valves here, and that'll either be nitrogen or clean compressed air. The pressure regulators here on single use, you may end up using a JSR LF LP, depending upon what the set point is here. On the single use regulators would be more likely than a JSR LF than the smaller valve. On this valve, this is going to be almost a blanketing type pressure reducing valve. And the JSR ULP is a great candidate for that because it's completely self-contained. I'd be setting this at 0.2 psi pressure. I think I misspoke earlier. A 0.3 psi on a 500 liter bag. That's 0.3 psi, not 0.3 bar. So this is going to be a low blanketing style regulator like this type of valve. Here's some photographs that I've taken over the years. This was at a bioreactor skid manufacturer in Pennsylvania. Love this photo because they neatly installed the gauges right above the regulators that were used. And you can see nitrogen here, carbon dioxide here, oxygen. And this is an industrial valve. That's a Jordan Mark 68G, and that's on instrument air. Typically, again, on stainless steel bioreactors, the JSR LF and JSR would be used. You can use these, but the extra features on this valve really aren't necessarily needed on this type of valve. So this is a photograph that one of our reps took at a gas panel manufacturer up in New Jersey. This panel ultimately went to a cell and gene therapy plant in North Carolina. And here, this was single use, but for whatever reason, they ended up using JSR LF valves on this panel. Here's another panel. This is a little bit better looking, a final form of a gas panel that's installed in a bioreactor suite wall. But you can see the JSR LP. This is probably, in fact, it was a gene therapy manufacturer in Massachusetts. So this is going to be a single use regulator here. Again, you can see the ball valves right upstream and sometimes downstream of valves, but always on a regulator upstream of the regulator. And there's a reason for that I will explain later. This was a gene therapy plant that was under construction in Boulder. We took the picture of this. These are the individual suites where these were 50 to 100 liter bioreactor bags that were going to go here. And they used JSR LFLPs on that application. This is an interesting one. This was a plant in the US Northeast. And here we've got ceiling mounted gas connections, and you can see all the gas lines coming down. And again, you'll see shutoff valves, sanitary ball valves upstream of the regulators that are here. So sometimes folks will do gas panels. And at the bottom down here, they've got quick disconnects for tubing. We'll come back to this photo later because I want to talk about something to be careful about when you're doing that. So you may have noticed here, we've got, instead of a mass flow controller on the CO2 line, we've got an Equilibar FD advanced flow control valve. This particular customer for this application found out that his mass flow controller did not quite have the turn down that it needed. And the Equilibar FD advanced flow control valve has a minimum 100-to-1 turn down, which is wonderful for this application. And it's also, the flow control on this thing is incredibly precise, and precise enough to get to accurately control the flow of CO2. CO2, by the way, on bioreactors is likely the only gas that's going to vary. Once the bioreactor is up and running, the bioreactor is inoculated, is seeded with cells. Typically, they will set clean compressed air and O2. And once they set that and get it right, that pressure is not going to change and that flow rate's not going to change. CO2 can change, however. CO2 flow is varied sometimes to control the pH of the bioreactor broth. So they'll either add additional CO2 or they'll lessen the flow of CO2 to control the pH in the bioreactor broth. So know that that's really the only valve where the flow is going to vary. And I bring that up because that comes into play when you're talking about the type of valve to use. We'll come back to that. All right. And on single use, the same thing. And here we see a single use Equilibar SD valve. And this is a completely single use assembly. This typically will be sold to a single use integrator that will integrate this valve into the tubing set along with the bioreactor bag. And then when it's installed, it's clamped into the stainless steel valve body. So we've got single use or stainless steel for precision flow. Let's look back on the stainless bioreactor, and we've got a back pressure valve downstream of the sterile vent filter that you see here. Typically, this is going to be a 958 or the JSB for back pressure, low pressure series regulator would work fine, or the Equilibar back pressure regulator would work well here too. So it can be anything. It's interesting to note that the sterile vent filter, as well as the sterile supply filter, this is our sterile barrier for gases on the bioreactor. So in actuality, downstream of the sterile vent filter, I really don't have to have a sanitary valve here. I could use a non-sanitary valve because this is the sterile barrier. However, most folks will use a shiny stainless steel valve if that valve is inside the bioreactor suite walls. If it's outside of the wall, you can use a non-sanitary valve. It's fine, again, because I've got a sterile barrier here. All right, moving on. This is the single-use back pressure Equilibar. This is the only single-use back pressure regulator on the market. And I like that in this position here, upstream of the sterile vent filter, and here's why. This valve, scientists, techs that work with bioreactors worry about bioreactor foaming. In the event of a foam event, what they're really worried about is that foam going through the tube and wetting the inlet of the sterile vent filter. If I've got an Equilibar SD single-use bioreactor bag here, the probability of that foam ever going through that valve and wetting the vent filter is much, much lower. We haven't tested this, but I think this is a great application, is putting it upstream of the sterile vent filter for that very reason. All right, let's look at the valves and how they work. This is the flow path through the valve, the blue. Gases come through. We've also got, this is the stem. The plug is the conical shaped part of the stem. This is the upper stem here, and it reaches all the way up to the lower diaphragm plate here. And on top of the lower diaphragm plates, it's the diaphragm. So I'm telling you all this and showing you this to to show how these valves work. So let's look at how do they work. Regulators are incredibly simple mechanical force balance devices. The outlet pressure, as you can see, is exposed directly to the underside of the diaphragm. So the outlet pressure is pushing up on the diaphragm. That force is opposed by the adjustable spring force. I turn the adjusting knob, I compress the spring, and I can put so many inch-pounds of force here on the top of the diaphragm, and it's pushing against the outlet force. So let's say I install this valve, and I'm putting air inside or nitrogen in a vessel, and I put 20 inch-pounds of force, right, about 1.2 bar force on the top of that diaphragm. I turn the gas on, open the ball valve, gas goes through, the valve's wide open because the spring force is pushing the diaphragm, the lower diaphragm plate, and the stem all the way down, and the valve's open. So gas rushes through here, fills that vessel. In a couple of minutes, the pressure in the vessel will rise, and eventually it'll rise to 20, but no more than 20 psi, because when it's at 20 psi, the force pushing up will equate to the force pushing down, and the valve will be in a stable flow position, maintaining an outlet pressure of 20 psi. Now, let's imagine for a moment that somebody opens a valve on the vessel and the pressure drops to 10, 15 psi. What's going to happen then is the spring force will take over, push the valve in the open direction, opening the valve more, letting more air in until that force balance, until that equilibrium is reached. That's how regulators work. All manufacturers, they all work the same way. All right, that being said, let's talk about some fundamentals here. Accuracy in pressure reducing valves is measured by what's called set point offset. If I set the valve, in fact, let's talk about this test curve here. This is a test curve from one of our data sheets. This valve was in all likelihood set at minimal flow, probably about 2 SCFM at right about here, set at 20 psi at a minimal flow. When they tested this valve, they of course increased the flow, and they looked at and recorded all what the outlet pressure set point did as they increased flow. You can see it drops down. This is typical. All pressure regulating valves exhibit this effect. If flow doesn't change, and let's say I set it at here at 35 psi inlet pressure, and I set it at 17 psi, as long as the flow stays the same, that valve will regulate all day long at 17 psi. It's only when flow changes or increases that you see the negative offset, which is called droop, because the curve is drooping. That's the Americanized English term for that. In the same way, if flow decreases from where you set the valve at, the set point will rise. And if I go to here, the set point will rise all the way to my 18 psi set point at 2 SCFM. To minimize droop, choose a spring so that the set point will be in the upper half of the spring range. All right, so look at here. I had here, let's say a 20 psi set point, and I used here 18 psi. I used a 15 to 25 psi spring. I want to choose a spring so that set point's in the upper half. If I had a 5 to 50 or a 5 to 25 spring range, I would rather use that here, but these were the test charts that we used. So I want that set point to be closer to the maximum set point allowable with the spring at the upper half of the spring range. So if my set point were at 24 or 25, this spring would be ideal. If it were at 22 or 3, I would choose this spring as well. So choose a spring so that the set point will be in the upper half, and it minimizes the amount of droop that you have. All right, seat leakage. So all regulators leak, right? And I can have a regulator that has class 6 shutoff. ANSI FCI and the IEC standard tell you that actually if it's class 6, that class 6 leakage is, the industry terms it as bubble type, but it's actually not, because a class 6 valve 1 inch and under can leak 1 bubble a minute, and that's still considered bubble type. You need to know that and integrate that into your thinking when you're applying valves in any application. And I'll show you why. On this application, I took this up at a vaccine manufacturer in Quebec, and this was in their formulation room, their cold storage formulation room. This is nitrogen coming down, going through a ball valve here, through our regulator, through a safety relief valve, past a pressure indicating gauge. There's another ball valve that I can't see. I can see that one, but there's another one that closes or opens flow to this blue flexible hose. And this blue flexible hose has a tri-clamp connection on the end. They would take that tri-clamp connection and hook it to mobile wheeled formulation vessels, 50 and 100-liter vessels that they would wheel into this space. They would then connect that blue hose to the top of the vessel. The tech would come over, open this ball valve. This valve was preset at 0.3 bar, 5 psi, and they would let nitrogen flow into that vessel and into the headspace on the top of that vessel. It would flow until the pressure reached 5 psi, 0.3 bar, in which case the regulator would close off because it had satisfied that pressure. The technician would close this ball valve. He would then uncouple the hose and he'd walk away. This is a problem. If I close this ball valve here and this ball valve is still open, I've got 90 psi on the inlet side of this valve, or 80 or whatever it was, inlet pressure on the inlet of the valve. This valve's working fine. It's class 6 shutoff. But if this guy, this tech, comes back an hour later, 2 hours later, there's a high probability that I'm going to have pressure beyond the set point in this line because of equalization of leak through. 1 bubble a minute. It's not going to take long to fill an 18 300 centimeter section of 3/4 inch tubing to raise the pressure. So for that reason, you've got to shut the ball valve at the inlet of the valve. Just remember that prevents equalization leak through on a service like this. And by the way, whenever you fill to pressure, this is called deadheading, is the term for that we valve guys use anyway. All right, here's another issue. You saw this photo below. When you disconnect a quick disconnect fitting, these quick disconnect fittings have ball check valves in them. So when they pull that hose off, a ball stops flow immediately to these check valves. Two potential problems with that. One, the next time they hook a hose up, if it's a couple hours later or a day later, there's a good chance that this section will be filled with gas at or near the inlet pressure because of leak through. It could be, all right? So you need to be aware of that. So close the ball valves, the inlet ball valves again. I sound like a preacher, I know, but it's important to know that for folks so that they don't do that. Secondly, when you quickly disconnect, just be aware that you're shocking this valve. That diaphragm on that valve, when they pull that quick disconnect, the diaphragm is going to fluctuate rapidly and it's going to open and close. You do that enough times, you could hurt the valve. We've beefed up our valve design based on that, so just be aware of that. But be aware of quick disconnects. And again, shut the ball valves at the inlet side, all right? One last term, and we're going to end because we're coming close. This, when valves, this is another curve, 5 to 15 psi spring on this one. On this test curve, when they shut the valve, they probably set this, and they did at 10 psi. You'll notice when flow gets close to zero, on some of the curves, you'll notice a big uptick in the pressure. This is called lockup. And in this particular valve, it's about 1.3 SI increase in pressure that you'll see at the curve. And the curves always have a little tail up. Just be aware of that increase in pressure. How do I minimize lockup, and how do I minimize and make sure my valves seat quickly? Choose the softest seat possible that you can. Our softest seat that we have is EPDM. The second softest is Teflon. The hardest plastic seat that we have, fluoropolymer seat, is PEEK. But if you choose a softer seat, you'll get shut off quicker, and lockup will be diminished because as the valve soft seat touches the orifice, it'll close quicker because the seat material is deforming to the seat, and lockup will be less. So that's a way to minimize that. So how else can I combat lockup? And I'll show you that real quickly here. Let's look at this is our valve cutaway illustration. Again, I want you just to refamiliarize yourself with a standard valve, no options. This is the lower diaphragm plate. Here's my valve stem, upper stem. You can see the upper stem fits into a little cavity on the lower diaphragm plate. These two move together, of course, but this is what the standard valve looks like. Let's look at a self-relieving valve next. Here's the cutaway of a self-relieving valve. This is the valve stem. Here's the plug, conical plug. This valve is closed because it's up against the soft seat washer here. You can see the stem on a self-relieving valve is the upper stem is sitting against this. This is a soft seat, a soft insert. We machine a little cavity in the upper diaphragm plate for self-relieving, and we put a little Teflon insert that has an orifice drilled through it, and that leads to a cavity that leads all the way up into the spring housing. Here's why we do that. Self-relieving, what happens when the valve is closed, the plug is against the washer, there's no flow going through this valve. I may have some leakage though, and if I do, if the downstream pressure rises above the set point pressure, which is the force generated by the spring, what will happen with the self-relieving valve is that diaphragm will lift. And when the diaphragm lifts, that here, it lifts the lower diaphragm plate, and that opens the cavity here. So all the downstream gases go into they escape into the spring housing chamber, and there's a little port on the spring housing chamber that leaks through. That's how you can combat pressure build downstream or equalization from deadheading or from lockup as well. So knowing that's great on clean compressed air, not a problem. On gases, that could be a problem if my regulator's in an enclosed space and it's nitrogen or CO2 or oxygen regardless. I don't want that pure oxygen venting out the valve handle, or I don't want nitrogen or carbon dioxide in a closed space. I can't because that displaces air. In those cases, make sure to also specify a captured vent option. And then with the captured vent, we put a little collar over the vent port on the side of the valve. By this sealed collar, we provide an 1/8 inch FDPT fitting there, and you can tube that gas away to a safe place to prevent any hazardous gas from getting out. Next, we're going to discuss questions about clean air system design as it relates to successful pressure reducing valve application. We'll also talk about some additional fundamentals about valve installation and commissioning. To do that, I'm going to pose some questions for you, and then we will talk about the answers. So question 1, is there a need for a primary pressure reducing valve, a PRV, to reduce the distribution line pressure upstream of the point of use? So the answer is typically no for clean compressed air or instrument air applications. With one exception, almost all of our point of use PRVs have a maximum inlet pressure for tri-clamper tube end valves of 150 psi, 15 bar. One exception, our JSR LF tube end and tri-clamp pressure gets up to 450 psi, and even higher, as you can see at the bottom, for NPT valves with different seat materials, up to 4,000 psi. So that being said, compressed dry air or instrument air is usually distributed between 80 and 120 psi, between 5.5 and roughly 8.3 bar. So a primary PRV is generally not required, nor is it desired. Why isn't it desired? Because all these point of use regulating valves operate at their highest flow range and least droop at high differential pressure. So the higher the inlet pressure is, the better. Looking at the chart on the right, let's look at the JSR LP chart. You can see the x-axis, airflow in liters a minute, or SCFM, the y-axis, outlet pressure. So these are charts similar to what we looked at earlier. Let's look a little bit deeper. Here, each individual curve, you can see, has a label. So P1, our inlet pressure on this curve, is 50 psi. This one, 75 psi. And this one at the far right is 100 psi. Look at the additional flow range that we get out of these valves with the higher inlet pressure. With the inlet pressure of 100 psi, we can get about 1550 liters per minute with a valve with an inlet pressure of 100 psi. Whereas the 50 psi inlet pressure curve, it ends at about 900, 950. So you can see as inlet pressure increases, I get more range out of the valve, and I also get less droop. This curve with an inlet pressure of 100 psi is a lot less droop than this one does at 50. All right. The same is true looking below at the JSRLF, just different inlet pressures. And this would be a graph you'd use if you had an NPT valve where we can go up to about 4,000 psi max. Look at the difference here. This curve has an inlet pressure of 1,000 psi, this one at 300 psi. Look at the additional range we get. And again, the less droop, the less negative offset. All right. So that's for compressed air or instrument air applications. For clean compressed gas, O2, CO2, nitrogen, it depends upon the source and distribution line pressure, but most of these, you're going to also be able to operate at highest inlet pressure. Bottled medical grade gas pressures are very high at the bottle, typically 800 to 3,000 psi, 53 to 200 bar. But they are usually reduced after the bottle, immediately downstream for distributions at pressures like for clean gas or clean compressed air. And that's usually, again, 80 to 120 psi. So typically, they're going to be at the same pressure. Same with gases evaporated from their liquid cryogenic state, their outside storage. Most of you are familiar with Linde or air products tanks, or they've got outside storage of liquid gases, and then you'll see an evaporator next to it. The gases are evaporated typically, and then they're knocked down a little bit for distribution at pressures like clean compressed air. All right. So regardless of the source, if the distribution pressure is above the point of use pressure regulator's maximum inlet pressure, typically 100 and greater than or equal to 150 psi, you will need to reduce it, but keep it high for the reasons that we described before. Question 2, what does the ideal clean air and gas point of use pressure reduction installation look like? How many PRVs are needed to ensure the pressure at each point of use? And you can see the ideal installation, which is illustrated here, is one regulator for each point of use, for each of the mass flow controllers that you see here. That's ideal. But in reality, that's hardly ever going to happen. If you can do it, great. But chances are cost and budget constraints aren't going to allow you to do one regulator for each point of use. So that being said, there are some practical design considerations that should be followed for successful application of one PRV for multiple point of use applications. So the best practice dictates that the flow requirements of all the point of uses downstream must conservatively fall within the capabilities of the regulator that's installed upstream. So in other words, you can install one regulator to service multiple points of use if that regulator can conservatively handle the maximum flow for all the points of use downstream of it and the minimum flow of any individual POU. So taking a look at the illustration at left, this is not okay. I've got one regulator servicing 8 points of use. In all likelihood, in all probability, that's not going to work. The regulator is not going to have a large enough range to handle all of these operating at maximum flow, or just one of them operating at a minimum flow. Highly improbable. Take a look to the right of that. We've got one regulator that's regulating the flow of gases to 3 different points of use. That's probably going to be okay. But you still need to verify that the total max flow for the entire drop and the individual minimum flows for any one of these are safely within the regulator's operating range. And of course, to the right of that, we've got one regulator for each point of use. That's definitely okay. But again, do that verification. Verify that regulator can handle the max flow of all 3 of these if they're operating at the same time, or the minimum flow if just one of them's operating. Regulator's got to be able to handle that, and that's how you would check it. So best practice, be conservative during design. Don't put too many points of use downstream of a regulator or it's going to come back and bite you. If we see issues during commissioning, most often it's because there's a mismatch between design flows and actual flows. Most of the calls that we get about my regulator's not working, well, in actuality, the regulator's fine. You're trying to get too much flow. You got to be careful about that. One of the neat things about our product line is that we publish an enormous number of flow versus P2 versus set point charts like those you're seeing here. On average, we've got 68 individual test charts per model. So in all likelihood, you're going to be able to find your specific application in our test charts. That's pretty cool. We did that on purpose, right? Lastly, we've got some tech fundamentals, additional fundamentals about installation and commissioning. Installation of our point of use valves, pretty easy. You can install them horizontally as shown at the top illustration, or you can also put them in vertical lines. And the plane of installation really doesn't matter. It's okay. Why is that? On gas pressure regulators, on liquid, you can't do that. On bioprocessed fluids or WFI, you can't do that because you're worried about drainability. In clean compressed air and gas applications, we're not worried about drainability because those gases are very dry, and we're not going to worry about drainability because there's no liquids in there. That's a little bit different if you're blanketing. On blanketing applications where I'm using gases to blanket the top of a headspace of a vessel, a little bit different because there I've got to worry about the fluid vapors condensing. But on these upstream point of use applications, you don't. You can install them vertical or horizontal. So here's another little best practice note concerning installation and commissioning. Several times a year, we receive regulators back at the factory from contractors with a request to clean and rebuild them. And the request usually comes before the system pressure test and after customers wring the lines out. They blow the lines down. When we take these apart, after we inspect them, almost always we find debris in the valves, orbital welding debris, cutting chips, and other solid contaminants. And I can tell you one time we found a cigarette butt embedded in a sanitary clean valve. You'd be surprised what you find in these valves. So why is all that debris ending up in the valve? It's because the contractors are wringing the lines. They're blowing the lines down through the valves. Air and gas regulators have tiny orifices. The smallest orifice in the clean gas tubing line upstream of the sterile filter. So any residual debris in the lines will collect in the valve and get embedded in the valve soft seat when they wring the lines down. For that reason, you don't want to wring the lines down with the valves installed. All of our regulators are either spec clean for oil free or O2 clean, shipped from the factory already thoroughly clean. They do not need to be blown out or cleaned. They've all been vibratory, ultrasonically degreased and inspected by blacklight if they've got clean for oil free or O2 cleaning. So you don't want to blow the lines down with the regulators installed. Instead, when you're blowing lines down, remove the regulator before the blowdown and install a clean sanitary tubing spool piece. We can make them, if any of you desire that, not a problem and relatively inexpensive. Or if you have a short section of tri-clamp end or Teflon line flexible hose, install that in their place. Don't risk delaying the project completion by having to remove the valves because they are loaded with tubing debris. Don't blow down through the regulators. Just a hint from an old factory guy. All right, a couple of final valve options I want to talk about, and then we'll be done. Air augmentation. A lot of you probably didn't know this, but all of these little point of use regulators, you can air augment those. So instead of having to adjust and compress the spring with the handle, you can load air into the spring housing and make the valve operate on the air that you loaded. Make that set point adjustable via air pressure. And I can do that by using another small regulator to load air into the spring housing, or I can use an I to P and I can completely automate that and do closed loop control for remote set point adjustment via the I to P and your PLC or distributed control system. It's worthy to note that either of those methods, air augmenting provides a significant reduction in offset droop. So if you have a specific application where droop is a concern, look at air loading these valves. As with any regulator, and that's process regulators also, all those you can get air loaded if droop is a concern. But just know that's available. Finally, another option we didn't talk about earlier are gauge port option. And with the gauge port option, you can get an inlet regulator or an outlet side regulator installed and shipped at the factory like that. So no need to install gauges with diaphragm seals downstream or upstream of these little gas regulators. Get the gauges built into the valve. And there's a lot of configurations that you can use to do that. And that's all, ladies and gentlemen. That's all I have for this webinar. I appreciate everybody that joined us. Thanks for the time.